Hello everyone, welcome to Electronic and Physical Basics. This is lecture 5. Today we will dive into the physics of electronic components, starting with resistors, capacitors, and inductors. In the next lecture, we will explore semiconductors, including diodes and transistors. But before we can truly understand how these components work and why they have the properties they do, we need to cover some fundamental physical concepts. For example, what is a material made of? What actually makes something a conductor or an insulator? We'll also have to study some strange phenomena, like why is an electron at the same time a particle and a wave? And also how do these properties manifest in a crystal structure? And much more. So, let's start right at the basics of the basics. So, you are all familiar with this classical representation of an atom. This model was first presented by Lord Rutherford in 1911, so more than 100 years ago. In this model of an atom, the atom is made of a nucleus, and you have electrons that orbit around it. So we now know that a nucleus is also made of neutrons and protons. Okay, but from the beginning, physicists knew that this model cannot be a correct representation of atoms, and this for two main reasons. In this model, you can see that the atom is depicted like a miniature solar system. Okay, you have electrons that orbit around the nucleus like planets orbit around the sun. But if atoms were really like this, how could they remain stable? Given that they experience, for example, billions of collisions per second in the air against other atoms, against other molecules. The electrons should be ejected and fly off in all directions. But they do not do that. Another deeper argument against Rutherford's model comes from the way electrons move around the nucleus and what it means for them when it comes to electromagnetic radiations. So let me be a bit more precise. I need my laser pointer. Look at this electron. It's moving around the nucleus. Okay. But from the point of view of an observer located here, the electron is going down and up and down and up and down and up and down and up and down. Okay? It's actually oscillating sinusoidally around a position, an equilibrium position, like electrons in antennas. And you know from our first lecture what happens when electrons oscillate around an equilibrium position in an antenna. They radiate energy away in the form of electromagnetic radiations. So in this case, let's say that the electron, or this one, moves around once per second. It shall emit a radiation wave, an electromagnetic wave, with a frequency equal to 1 Hertz. If the electron would be going around 10 times per second, it would emit an electromagnetic wave with a frequency equal to 10 Hertz. Okay, that's interesting. Now, if the electron loses energy, what shall happen? The electron should spiral down and collide with the nucleus. And this would take, it's actually possible to calculate this, only a fraction of a second. Okay, so much less than what we see around. Okay, the atoms we see around, some of them are billions of years old. So how can this be? Well, this fundamental question was one of the issues that led to the birth of quantum mechanics. To explain the stability of atoms, like quantum mechanics do, we must consider the electron as something completely different, something we cannot even visualize. So listen carefully. According to our most advanced theories, the electron must be seen as both a particle and a wave. Experiments, and yes, I mean experiments, something we have been able to measure in a laboratory, have shown that electrons sometimes behave like waves and sometimes like particles. Let's take some examples. In the cathode ray tubes, of all TVs, the impact of electrons on a phosphorescent screen produced light and formed images. So in that case, electrons have to be considered as tiny pellets, okay, particles. But electrons can also be diffracted, for instance, by crystalline structures, in which case they behave definitely like waves. You know that from wave optics. So to make things even more complex now, the waves we are talking about here are not like waves on the surface of a swimming pool or the surface of the ocean. No, the waves we are talking about here when it comes to particles are, listen carefully, probability waves. Returning to the swimming pool analogy, the peaks and troughs representing where the water is displaced the most in one direction or in the other one, up or down. This would correspond, in the case of an electron, to the locations where there is the highest probability of detecting it. So this is crucial to keep in mind. Electrons are best described by probability waves. And like all waves, these probability waves can interfere both constructively and destructively. It is this interference that ultimately explains the stability of atoms. We will see how. But it also explains why semiconductors have gaps. And we will talk about this in the next lecture. Okay, you can see in this animation what happens when two waves interfere. I'll let you watch for a few seconds. You should know already what it means, interference, from the wave optic parts of the last lecture. But just in case, have a look again. This is a nice animation. Okay, you can see two waves. One blue wave going to the left, propagating to the left, and one green wave propagating to the right. Please note that both waves have the same velocity, and they also have the same wavelengths, which by the way means that they have the same frequency, and they also have the same amplitude. I've made some snapshots of the previous nice animation. These are the two most important cases. Let's start with the first one. Here, the waves perfectly overlap. Okay, and we say in that case that the two waves are in phase. Okay, the phase difference between both waves is 0 degree or 360 or 720. So the phase difference is an integer multiple of 360 degree. In that case, again, the two waves perfectly overlap. And what happens to the amplitudes? Well, the amplitudes of the two waves add together. Okay, the amplitude of the red wave here, which is the sum of both waves, is twice bigger or is twice the amplitude of the green wave or of the blue wave. Good. In that case, we call it constructive interference. Now, when the waves are perfectly out of phase, what you have here, the phase difference is 180 degrees, which corresponds to a shift of half a wavelength. And here, as you can see, the two waves perfectly cancel each other out. Okay, the resulting amplitude of the red wave, so the resulting amplitude from adding the two waves, is 0. This is called destructive interference. So the phenomenon of interference is extremely important in science and technology. It appears absolutely everywhere. Okay, electromagnetics, optics, acoustics, quantum mechanics. As soon as you have waves, you get interferences. Okay, let's now see what happens when waves propagate along a string fixed at both ends. We have this here. The string is fixed at both ends. Well, in this case, a wave traveling in this direction, okay, to the right, will get reflected by the wall. And the reflected wave will, on its way back, do what? Well, it will interfere with the wave emitted to the right. Okay, so if you continuously excite here, you will continuously send waves to the right, and these waves propagating in this direction will continuously interfere with the reflected ones. So we have here a wave which is folded, if you want, a wave which interferes with itself. And if everything is right, that is, if the wavelength has the right length, okay, you can see here 1/2 wavelength, 1 full wavelength, 2/3 of a wavelength, 2 wavelengths. Okay, so if the wavelength has the right size in comparison to the length of the rope, you get this very nice phenomenon you are looking at. You get resonance mode. In our case, this mode is called the fundamental, and these 3 modes are called the harmonics. Well, now something very important. If you go up, the frequency increases. But it also means that the energy increases. And at the end, what are you looking at? You are looking at a resonance cavity which allows only discrete values of frequency. You can see here, okay, we just have these 4 modes which are possible. In between, nothing. So only very precise frequencies, okay, can exist inside this cavity, and the other ones just cannot. Now, do not forget that frequency is also linked to energy. What we have now is a set of energy levels which are allowed in the resonance cavity. Good. Now back to our electrons. You know that electrons are kind of a wave. And this wave is going around the nucleus and it is closing on itself. So it's like having this string closed on itself and waves propagating along it. And so these electron waves, they will interfere with themselves and also give birth to resonant modes, to harmonics, to energy levels. Okay, so you all know that atoms have electronic levels inside, and electrons can jump from one level to the other one. Well, this is the reason why. Okay, only when everything is right at some specific distances from the nucleus will you have the electron wave close nicely on itself and give birth to constructive interferences, so to harmonics. Between the levels, you do not have this condition. It's not fulfilled. Okay, so you have destructive interferences. You have nothing. The electron cannot be there. And don't forget that actually these interferences, if they are constructive, it means that the amplitude of the wave is not zero, and the amplitude of the wave is the probability to have the electron there. So if you are between the levels where interferences are destructive, the amplitude of the electron wave is zero, which means that you cannot have an electron there. Now you know where the electronic levels in an atom come from. All right. In summary, it is the wave-like nature of electrons and interference phenomena that explains the existence of electronic energy levels in atoms. So this is heavy. Let me tell it once more. It is the wave-like nature of electrons and interference phenomena that together explain the existence of electronic energy levels in atoms. Okay, it's an energy spectrum. Only specific levels are allowed where you can find electrons. In between, you cannot find them. And this explains why the atoms are stable, why the electrons cannot spiral into the nucleus. Okay, they are trapped in these levels. They cannot exist in between. So they cannot spiral down to the nucleus. And the levels are the only places where they can truly exist. Okay, but now be careful. The waves we are talking about are actually three-dimensional, not one-dimensional or two-dimensionals. They are three-dimensionals. And so are the interference patterns. So it's not exactly like the case of a string fixed at both ends. The interference patterns are what we call spherical harmonics. And you can see some examples here. So these are known as atomic orbitals. That's a term that is very important in physics. So once again, what you see here are three atomic orbitals, three interference patterns in three dimensions. So interference patterns of the electron cloud or of the electron wave. So now, once again, these nice clouds. Okay. So the lobes here, they show you the regions where the probability of finding electrons is not zero. They indicate where electrons can be found when we attempt to detect them. Okay. So, the first atomic orbital on the left is completely spherical. It is called an s orbital. The second here, with two lobes, is a p orbital. The third one here on the right is a d orbital. Now pay attention. The lobes here of the second orbital, of the p orbital, they could also point along the x-axis and also along the y-axis. So we have three possible p orbitals with the same energy. We also have actually 5 possible d orbitals. Just trust me on this one. So in summary, electrons are described as or by probability waves. These waves can wrap around atomic nuclei and interfere with themselves, producing interference patterns called atomic orbitals. Only certain patterns can exist, and each has a distinct, well-defined energy level. Again, this is the origin of the discrete spectrum of atomic energy levels, as illustrated in the following figure. Yes? So this slide here is very important, okay? It summarizes what we have just studied. It is important to note that the energy of the p orbital here is slightly higher than that of the s orbitals. And also the energy of the d orbitals, is a bit higher than the energy of the p orbitals. So there is an order and organization of the orbitals, as you can see here in this figure. So we won't go into further detail here, but you may have also noticed that the fundamental, so the first energy level, contains only one s orbital. The second energy level, this one, contains one s orbital and not one p, but the three p orbitals. I haven't put them on the slide, but please keep them in mind. We have three p orbitals here. So one s and three p orbitals in level 2. Now, what about level 3? Here we have one s orbital, three p orbitals, and 5 d orbitals. Okay, here is a new figure that summarizes the order of the orbitals up to level 7. So you can recognize what we have already learned. We start with the 1s orbital, then move to the 2s, followed by the 2p orbital, then the 3s, and so on. Okay, so this brings me to the point I have been leading up to from the beginning. Okay, the order of the orbitals actually determines the filling of atomic energy levels by electrons. Okay, it tells you how electrons populate the existing energy levels one after the other. So they start by filling the 1s level, then the 2s, then the 2p, then 3s, okay, then 3p, then actually 4s. I will not go into details here, but the 4s orbital has an energy slightly lower than the 3d orbital. So the 3d orbital come next, then the 4p, 5s, 4d, etc. You just have to follow the arrows. Good, so now we know in which order the levels are going to be populated by the electrons. But you might ask, yeah, right, but now I also need to know how many electrons I can pack or per level or on one given level. And you're right, this is a very important question. And to answer this one, we need one more fundamental principle of nature, and this is the famous Pauli exclusion principle. So Pauli was an Austrian physicist who made major contributions to the development of quantum mechanics in the first half of the 20th century. He was an absolute genius. He was awarded the Nobel Prize for the discovery of this fundamental principle of nature, which now bears his name. Listen carefully. No more than 2 electrons can occupy the same orbital. One with spin up and the other one with spin down. So I will not go into details here, but spins tell you, the rotation direction of your electron. So if you picture an electron as being a small ball rotating around an axis, it can, rotate clockwise or anti-clockwise. And in one case, the spin is said to be up, and in other case, it's said to be down. So we won't go into further detail here, as mentioned. So please just remember Pauli's rule. Only 2 electrons per orbital, not per level, per orbital. So now, with this principle, we can now correctly fill the atomic energy levels, the electronic energy levels in an atom once we know the number of electrons in a given atom. Good. Let's try it in one example. I selected zinc as an atom randomly. Zinc is interesting here because it has many electrons. Zinc has 30 electrons. So how will these electrons feel the electronic levels in the atom? Well, we will get first 2 electrons in the 1s orbital. So there are 2 electrons in level 1. Next, 2 electrons will populate the 2s orbital, followed by 2 electrons in each of the 2p orbitals, giving a total of 6 electrons in the 2p orbitals. Now we have 3 of them, so 3 times 2 equals 6. So we have in total 8 electrons, 2 plus 6, in level 2. Moving on to level 3. Level 3 contains 1 3s orbital, 3 3p orbitals, and 5 3d orbitals. So we place 2 electrons in 3s, 6 electrons in 3p, and 10 electrons in 3d. This gives a total of 18 electrons in level 3. So far we have placed 2 plus 8 plus 18 electrons, that is 28 electrons. Only 2 remains. And they will of course populate level 4s. But then you might tell me, but you told us that actually level 4s has an energy level below the one of orbital 3d. So what happens here? And you would be exactly right. Actually, the 2 electrons will populate the level 4s before the 18 electrons populate level 3d. But at the end, we have the same configuration, right? So what you see here is actually the standard electronic configuration as given in chemistry books. So you can see that zinc has a structure of argon plus orbital 3d full with 10 electrons and orbital 4s full with 2 electrons. So we say that zinc has an electronic configuration argon 3d10 4s2. Take a few seconds to check this and learn about it. Okay, so there you have it. The energy levels are filled, and we now know the electronic structure of zinc. Before moving on, I would like to give you a small exercise. Try to determine the electronic structure of oxygen and then that of hydrogen. Of course, you should start with the number of electrons for each atom. If you don't know, you can look it up online. Then use the rules we have just studied to fill the atomic energy levels or the electronic energy levels in oxygen and hydrogen. So it's your turn now. We will meet back in, let's say, 5 minutes. So please do it. Draw the energy levels and fill them with the electrons. Do not ask ChatGPT, do not check on internet. Do it yourself. It's a nice exercise. And also it's completely fine if you don't get it right. But please at least give it a try, and a serious one. Okay, let's go. Let's take 5 minutes, starting with the atomic structure of oxygen. So I will not wait 5 minutes. Just stop the video, take your time, plot the levels, like you can see here, and populate the the electronic levels one after the other. So I give you already here the beginning of the answer. So oxygen has 8 electrons. The symbol for oxygen is O816. At least that's the most common form of oxygen. We are not talking here about its isotopes. So oxygen has 8 electrons, and please put them where they belong. Okay, let's say that you stopped the video, took the 5 minutes and did the exercise. So 5 minutes are now up. Here is a solution for oxygen. We have 2 electrons here in the 1s orbital, 2 electrons in the 2s orbital, and the 4 remaining electrons in the 2p orbital. Arrows are here to express the orientation of the spin of the considered electron. And you can see that when you have 2 electrons populating one orbital, one has to have spin up and the other one spin down. Okay, so we have here pairs of electrons. These 2 electrons are still alone in their respective orbitals, so they could take also the down or be down spin or spin down, or one up and the other one down. This doesn't matter here. Good. Now, I hope you also took the time to think about the electronic structure of hydrogen. This is super easy. Here we just have 1 electron, so this is the electronic structure of hydrogen. It's 1s1. All right, we've made good progress, and now we are ready to move on to the next exciting step. It's actually time to understand how molecules are formed. Nothing less than that. Well, there is just one more law of nature we need to know, and it is this one. Atoms, okay, like to have the highest energy shell completely filled. Okay, by shell here I mean the highest energy level, the highest orbitals. So this rule is very, very important. To actually fill the outer shell, atoms have different possibilities, and this is what gives rise, as we will see in a few minutes, to the various types of molecular bonds. And these bonds explain the structure of many materials, and therefore also most of their physical properties. Let's take an example. We have already determined the electronic structure of oxygen and hydrogen. So oxygen really wants to complete its outer shell, which here is a 2p orbital. So it is missing actually how many electrons to do that. Just think about it a few seconds. And we have 3 2p orbitals. So we should have 6 electrons in this 2p orbital to have it completely full. So oxygen is missing 2 electrons. And oxygen will do everything it can to get them. Now let's look at hydrogen here. It is missing just 1 electron to complete its 1s level. So hydrogen will therefore do everything it can to gain one electron. So nature offers hydrogen and oxygen a very interesting solution to achieve that. It's kind of a compromise. Atoms can share electrons. That is, they can have electrons in common. Okay, this is very, very important. Atoms can share electrons. So in our case, two hydrogen atoms, let's say, offer to share the single electron with one oxygen atom. Okay? And the oxygen atom shares one of its 2p electrons, or let's say one of its remaining single 2p electrons, with each of the two hydrogen atoms. So oxygen shares this one with this hydrogen atom and this electron with this hydrogen atom. Okay? And hydrogen, this hydrogen atom shares its electron here with oxygen, and this hydrogen atom shares this electron with oxygen. Good. So oxygen thus gains two electrons, and each hydrogen gains one electron through sharing. This is a very good solution for everyone. And this very good solution for everyone is a chemical bond, specifically called a covalent bond. And what is the molecule formed in our case? Now that we have one hydrogen bonded to oxygen and another hydrogen bonded to oxygen through sharing of electrons and filling of the highest energy levels for each of the involved atoms. What is this molecule where we have two hydrogens and one oxygen? Yes, it's water, H2O. So here is another example of a covalent bond. Here, each hydrogen atom needs to gain one electron, but a hydrogen can also share its electron with another hydrogen. Okay? That's what you see here. So the electron which was orbiting this nucleus, this proton, now does this. Okay? It's orbiting both nucleus, so both protons. Okay, because hydrogen is made of just one proton and one electron. And the electron which was orbiting this proton is now also doing this around. So we have these two electrons, one with spin up and the other one with spin down. They are orbiting both protons. And this is a stable bond. It's a covalent bond. So now this molecule is stable, okay, and it's called dihydrogen. It's a famous H2 molecule. Now there is another way for an atom to complete its outer shell. It can either take an electron from another atom or give one away. For example, if it has only a single electron in its outer shell. By losing that electron, it can end up with a completely filled shell below. Okay? So, an atom that steals an electron from another gains an extra negative charge. It now has one more electron than protons, so the atom is no longer neutral. It becomes a negatively charged ion, called an anion. Conversely, an atom that gives away an electron loses a negative charge and becomes positively charged. It's called a cation. So of course, the optimal situation occurs when an atom that wants to gain an electron meets an atom that wants to lose one. then everything works out perfectly. Both atoms benefit. And this is exactly what happens when a chlorine atom meets a sodium atom. Two ions are formed, Cl- and Na+. And as you know, opposite charges attract each other, and strongly. So Cl- and Na+ strongly attract each other after having exchanged electrons. This forms what is called an ionic bond. And you also know the materials that result from the strong bond between Cl- and Na+. It is, of course, NaCl. That's table salt. So the two types of bonds we have just seen, the covalent bond and the ionic bond, are both strong bonds. It takes a lot of energy to break them. As indicated here, okay, it takes between 150 and 500 kilojoule to break 1 mole of covalent bonds, and between 170 and 1500 kilojoules to break 1 mole of ionic bonds. So we can see that it often takes even more energy to break ionic bonds than covalent bonds. So on average, the ionic bond is stronger than the covalent bond. Okay, we've just talked about strong bonds, but there are also weak bonds in nature. And these weak bonds are extremely important for many phenomena, including life. The biochemical processes that occur continuously in our cells require bonds that can form and break easily. So I will now mention two weak bonds. The first is a hydrogen bond. Let's return to our water molecules. We saw that the water molecules forms through the sharing of electrons between hydrogen and oxygen, but in reality, oxygen attracts these shared electrons more strongly than hydrogen does. So as a result, the electron cloud, or rather the orbital containing these two electrons around both atoms, is distorted towards the oxygen. There is more of it around oxygen than around hydrogen. Okay? So the electrons spend more time near the oxygen than they do near the hydrogen. Oxygen, as a consequence, acquires a slight negative charge, and hydrogen a slight positive charge. And since opposites attract, the oxygen of one molecule will attract the hydrogen or hydrogens of another one, and so on. That's what you see here. Okay? So all the molecules become connected by this weak hydrogen bond. So because of this bond, which does not exist in molecules like CO2, for example, and so between molecules of CO2, it takes more energy to vaporize water than to vaporize CO2. Okay, this hydrogen bonds, this chemical bond is weak, but it's not zero. Okay, so again, it takes more energy to vaporize water than to vaporize CO2. And why is it that important? It is actually the reason why water remains liquid at room temperature, while CO2 is already a gas. Because you need to give water more energy than you need to give CO2 to break the bonds between the molecules and vaporize them. So that's the reason why water at 20, 30, 50 degrees Celsius is still a liquid. Okay? It's not warm enough yet to break these extra hydrogen bonds. So CO2 is already a gas at 20, 30, 40 degrees, but water is not. And you can appreciate the significance of this small bond, because without this small bond, we simply wouldn't be here to discuss it. We just wouldn't exist. There would be no no liquid water around us at the temperature, at room temperature. So life, as we know it, would never have been able to develop like it did. Okay, I would now like to talk about another very important weak bond. This is the van der Waals bond. Its mechanism is somewhat similar to that of the hydrogen bond. In a water molecule, the slightly positive H, so hydrogen, and slightly negative oxygen, they form a dipole. Okay, what I explained before, the fact that electrons are more attracted towards O than towards H, it generates a charge, a negative charge on O and a positive on H. This is actually a dipole. And two nearby dipoles, as you see here, they can attract or repel each other. Look at what happens between the minus charges, the plus charges, the minus plus charges, the plus minus charges. Okay, so these dipoles can attract or repel each other depending on the balance between electrostatic attraction and electrostatic repulsion. So this force is very important in biochemistry and other phenomena. It is especially significant as a force between two surfaces in contact. For example, the skin can adhere to surfaces thanks to van der Waals forces. In the case of, small geckos, this force allows them to climb vertical smooth surfaces. Their fingers are covered with lots of skin due to this folded structure. So when they press a finger against a glass surface, much of this skin comes into contact with the glass, creating enough adhesive force to support their lightweight bodies. And so they can climb up. Great. Now we have just one more bond to study, but it's a very important one. It's the metallic bond. So here you can see possible arrangements of atoms which are typical of metals. We will see later that these are periodic arrangements characteristic of crystalline structures. But what interests us today is how the atoms are bonded to each other in a metal. So in a metal, the outer shell electrons, also called valence electrons, are freed from the atoms, which then become positive ions. They just lost electrons, the valence ones. And these free electrons, they can move freely throughout the metal. They are delocalized. So we say that the ions float in a sea of electrons. And similar to a covalent bond, where orbitals cover two atoms and hold them together, these delocalized electrons, they provide cohesion between all the ions. So in a way, the sea of electrons holds all the metal ions together. You can see here an example. So we use again sodium. You know that sodium atoms want to lose the outer shell electron. So what they do when they come together, when they are packed together, they form a crystalline structure and they all lose the outer shell electrons, which are now free. They move around, and this sea of billions and billions of electrons, they bond together the billions and billions of sodium atoms, which you can see here. Good. And actually this cohesion is very strong. In fact, I think I have it here. Yeah, it takes between 68 and 850 kilojoules to break 1 mole of metallic bonds. So on average, the metallic bond is also stronger than the covalent bond. And this very particular property of metals alone explains most of their physical properties, as we will now see. Okay, so when I teach this course in person, I ask these questions one after the other. And generally, students are able to give the correct answers based on what we've just learned. So, I ask them, why have metals high melting point? Why are metal very good electrical conductors? Why are they very good thermal conductors? Why do they have high density? Why are they malleable and ductile? But well, since this course is online and in blended learning, I will pose the questions and wait about 10 seconds before giving the answer to give you some time to think. So let's start with the first question. Why do metals have a high melting point? Why do they require so much heat to melt? So I guess you have the answer because I usually get the right answer from my students. So yes, metals require a lot of heat to melt because the metallic bond, which holds a solid metal together, is a strong bond. So to melt a metal, you must break this cohesion and therefore break these strong bonds. So that requires a lot of energy, between 68 and 850 kilojoules per mole, which corresponds to very high temperatures, to high temperature to very high temperatures. So next question, why do metals conduct electricity so well? Or let's put it another way, why is the electrical resistance generally very low? So answer, this is due of course to the presence of a huge number of free electrons in the metal. Electric current itself consists of electrons that can move very easily through the metal. Next question, why do metals conduct heat so well? This one is a bit less obvious. So to understand it, we first need to understand what heat is. Heat is motion, agitation. Within a material, the more the atoms are agitated and moving, the higher the temperature and the more heat is stored in the material. Heat transfer is a transfer of this motion, this agitation. In metals, free electrons help transfer motion from one place to another. But the main reason metals are good thermal conductors is their crystalline structure. In a crystal, atoms form a well-ordered three-dimensional lattice which vibrates easily, and vibrations are easily transmitted from one point to another. So mechanical agitation and therefore heat is easily conducted from one point to another one. Next question. Metals are high density materials. Why? Well, there are actually three main reasons. First, the atoms are well organized in the crystal lattice. They form a compact arrangement. You saw this in the previous slide. Okay. Second, the atoms are held together by strong bonds, which also contributes to a dense structure. And third, the atoms themselves, gold, silver, copper, iron, are already quite heavy. So these three factors combined explain the high density of metals. Last question, why are metals malleable and ductile? This is a rather surprising property of metals, okay? But you probably know that it is quite easy to deform gold or silver. Why? Well, again, the reason lies in the metallic bond. As we explained, it is a very special type of bond. A sea of electrons holds together metallic ions, and the ions are not directly bonded to each other. So this structure is relatively easy to deform because you do not need to break bonds between atoms to change the shape. That's it. Et voilà. Okay, now you're probably wondering, why is steel so rigid? Why is it so difficult to deform in comparison to gold or aluminium? Well, to understand that, we first need to talk about dislocations. The crystal lattice in the middle is actually far from perfect. There are defects like you can see here. Okay, that's one defect. You can see one atom is missing, and this generates a defect in the crystal lattice. Now, when a mechanical load is applied on the lattice, this dislocation will move, for instance, to the right. And the dislocation will jump from one side to another. To, let's say, cope with the applied stress. Okay, so actually what happens when you pull on a piece of metal, okay, you deform it, right? But you are not pulling the atoms apart from each other. What you're actually doing is you are making dislocations, billions upon billions of dislocations, move, okay, from one side to other sides. By doing that, the crystal manages to rearrange itself, okay, to cope with the applied stress. That's what's happening actually. And that's the reason why it's quite easy to deform pure metals. Okay, because it's easy to make dislocations jump from one side to the next one. Okay, so you can have a look here again and check what happens. So you can see that the dislocation jump to the next side, to the next, and you can see what happens at the end. It's like the whole lattice got deformed, let's say. Okay, you had first atoms here, and you do not have them anymore. They all kind of jumped to the left. Okay, so that's the message. You can see that the movement of the dislocation can make the geometry change, which is like saying that you just deformed your lattice. Okay, so I'm pretty sure now you got the idea. There are some very nice videos available on YouTube where soap bubbles stacked on top of each other are used to show the movement of defects in a lattice. They are really good, and I will let you search for them yourself. I mean, you can use, for instance, the keyword bubble raft. Okay, so now let's go back to steel. Steel is not made of iron alone. Okay, you of course all know that already. Steel also contains a small amount of carbon. And these carbon atoms distort the crystal lattice, making it more difficult for dislocations to move. But now, if the motion of dislocations is blocked, the metal becomes much harder to deform. This is why steel is significantly more rigid than pure iron. So now I have a short explanatory video for you. It's an excerpt from a video by the YouTube channel Veritasium. It's a very good video, and I highly recommend you to watch it if you haven't seen it already. So you can find the link to the video on the slide, to the full video on the slide. And I'm now going to play this short excerpt. Okay, so let me start the video.
Pure iron is actually softer than bronze, so in its elemental state, iron provides no advantage. But nature gave humans a lucky break. One of the few ways you can heat something up to 1250 degrees is with charcoal. And charcoal is basically pure carbon. And if you add just a little bit of carbon to iron, it creates an incredibly strong alloy, steel.
Yeah, a lot of people see it as a heat process. I see it as a chemical process.
Alloys are usually stronger than pure metals because they contain different sized atoms. And this reduces the ability of atoms to slide past each other when an external force is applied.
Okay, so we are at the end of the first part of the course. See you in the next video.